Suppose we have a system in the grand canonical ensemble, which means that it's characterized by the volume V, by the temperature T, and by a chemical potential, which is mu. And what we want to find is the number of particles in the system, and we want to find the energy. In particular, we want to find the expectation values of those quantities. What do we know about the system? Well, for fermions, we know that the single particle energy states are occupied with the Fermi-Dirac distribution function. So NFD, which depends only on the energy, is given as 1 over e to the power beta, which is 1 over kt as usual, minus mu, plus 1. And having this distribution function at our disposal, we can indeed find the number of particles and the energy. To find, for example, the particle number, which we commonly denote as n, we sum over all the quantum states of single particles. So J is a single particle quantum state. We sum over all of those, and then we multiply by the probability that those states are occupied, which is nothing but the Fermi-Dirac distribution. So we have e to the power beta, and then the energy of state J, minus mu, plus 1. And so this gives us the number of particles. A similar procedure gives us the total energy, which is calculated as a sum over all the single particle states, J, and then we take the energy of state J and we multiply it by the probability that there is a particle in that state, and that is given again by this Fermi-Dirac distribution, beta epsilon J minus mu in the exponent plus 1. For bosons, we carry out the same procedure, but now we replace the Fermi-Dirac distribution, which has a plus 1 in the denominator, by a minus 1. And apart from that, the expressions on the right-hand side for the bosons are the same as those on the left-hand side for the fermions. So the problem is then reduced to summing over all the single particle states, and that's the topic I want to address in this movie. So the problem addressed here is how to sum over all the single particle states, and we will focus here on the case of a single particle in a box. And we start with the simplest case, a box in one dimension, which is just an interval. Here you see the potential which is felt by the particle. It goes to infinity for x smaller than 0 or x larger than L, and between the two the particle has a potential which is 0. We know the solutions of the Schrödinger equation for that case. The lowest state is the one where we have just half a sine wave, and then the second state, I will take a different color, that will be a state which gives you a full sine wave over the interval between 0 and L. All these states are known analytically, and they are labeled by J, and they have the following form. The x psi j, which is just pi j is a function of x, is the square root of 2 over L, and then the sine of j times pi times x over L. So j is 1 corresponds to the black solution here, and j is 2 to the sine solution, the red one. All these states have an eigenvalue, that's an energy eigenvalue, hence Ej, and the Ej in this case is h bar squared, j squared, pi squared, divided by 2l squared. And you can verify this by taking such a solution and plugging it into the one-dimensional Schrödinger equation for a particle in a box. It's a standard example which is covered in any quantum mechanics course in the very beginning. The j here run from 1, 2, 3 all the way up to infinity, and therefore if we sum over the states, then we can write this as a sum of j running from 1 to infinity, and we assume that we are summing up some function which depends on j fj. And now we assume that there are many contributions, significant contributions for j's to this sum, and that f is a rather smooth function of j. So f depends only smoothly of j. And in that case, we anticipate that we can approximate this sum by an integral running from 0 to infinity of x. So we can write this as an f now of the continuum index x rather than the j. And the fact that I have replaced the 1 here as a lower bound by the 0 doesn't really matter if we have many contributions, significant contributions of the fj's to the sum. Instead of summing over j, we can also sum over the wave vectors. Recall that the solution to the Hamiltonian, which was x psi j, was given as the square root of 2 over L times the sine of pi jx over L. That can also be written as square root 2 over L sine kj times x, where the kj is now defined as j times pi over L. And that gives us an equidistant grid of kj's, and the spacing between the two subsequent k values, delta k, is given as pi over L. So instead of writing the sum over the j of fj, we could also sum over the k's, so over the kj, and then write f as a function of kj. And because we know that this is delta k, it is useful to write the following. First L over pi times the sum over kj, then f kj times delta kj, where kj is the spacing between the kj's, and this expression can be written as an L over pi times the integral of f k times dk. And the reason is that this expression here, the sum over kj with the delta kj, is a Riemann sum, which is an approximation of that integral. And of course, as usual, we suppose that fk is a smooth function of k. Obviously, the integral runs from 0 to infinity, just as was the case with the x before. For the particle in the box, we know that the wave function vanishes at 0 and L. We can also choose periodic boundary conditions instead. And if we do that, then we have the following boundary conditions. The psi 0 should be equal to the psi L. And also their first derivatives, d psi dx, evaluated at x is 0, should be the same derivative, d psi dx, at x is L. We can then find two types of solutions. The first is the square root 2 over L multiplied by sine 2 pi jx over L. And the second kind is the square root of 2 over L times cosine of 2 pi jx over L. And we can, of course, use these solutions, that's no problem, but we can also combine them into a new solution, which is the psi j of x being now a complex exponential, 1 over square root L e to the power 2 pi I jx over L. And it's important to note that here we only have positive j's. In the case of the sine solution, we can have j is 1, 2, 3, etc. And for the cosine, we have j equal 0, 1, 2, etc. So j is 0, and we have j is 1. We have that twice, 1 for the sine and 1 for the cosine. And then we have 2, etc. up to infinity. In this case, we have j is minus infinity up all the way up to 0. And then we continue with positive values all the way up to plus infinity. If we take the exponential solution and we take positive and negative j, then we can combine them into either the sine or into the cosine. And if we have the sine and the cosine, we can combine them into the exponential. And therefore, it's completely equivalent whether we use exponential waves, so plane waves, or whether we use sine and cosine. And we prefer usually to use the plane wave solutions, the exponential ones, because they are more convenient to work with. Obviously, we can introduce wave vectors for these solutions as well. We can write the sine of kjx. We can write the cosine of kjx. Or the exponential of I kjx. In all cases, because the kj is always given as 2 pi j over L, we have that delta k is 2 pi over L. Therefore, if we have some function f that we want to sum over all the plane waves, then we can write this as a sum over j. If we use the plane waves, then we see that j runs from minus infinity to plus infinity. But that is the same as the sum over kj, running also from minus infinity to plus infinity. And we now perform the same trick as before. We multiply this by 1 over the spacing in the k vectors, and then by the spacing itself. So that means we have L over 2 pi, which is 1 over the delta k, and we fix that by inserting an extra delta k in the sum then we recognize this sum together with the delta k as a Riemann sum, and we can write this as L over 2 pi. And now we have an integral running from minus infinity to plus infinity of fk dk. So in summary, we see that for fixed boundary conditions, a sum over all the states is given as L over pi times the integral from 0 to infinity of fk dk. And for the periodic boundary conditions, we have L over 2 pi, which is only half this prefactor. But in contrast, the integral runs from minus infinity to plus infinity. In nearly all the cases where we carry out such sums, it happens to be the case that this function f is an even function of k. And in that case, we can write this integral from 0 infinity to infinity as 2 times an integral running only from 0 to infinity, and then we immediately see that the two are equivalent. So we see that the two integrals are in that case the same, and fixed boundary conditions turn out to be completely equivalent to periodic boundary conditions. If we are dealing with free particles, then we have that the energy of those particles is given as h squared k squared over 2m, and we see therefore that there is a almost one-to-one relation between the epsilon and the k. We can use this in order to rewrite the integral over k as an integral over epsilon, and the most convenient one we can take is this one, the integral which runs from 0 to infinity, so we have L over pi integral 0 to infinity fk dk, and using this relation between epsilon and k and the fact that k is only positive in this case allows us to rewrite this as follows. We have L over pi and then an integral from 0 to infinity. Then we have our f of k. And then we can rewrite the dk as a dk d epsilon times d epsilon, which invites us to write the f also as an integral over, or as a function of epsilon. So we have f epsilon, and then we have dk d epsilon, which from this relation is easily found to be 1 over h bar square root m over 2 epsilon d epsilon. Obviously, f as a function of k has a somewhat different form than f as a function of epsilon, so I can put a tilde here in order to fix that. And what we see is that we can write the final integral, the final sum over all the states, as an integral from 0 to infinity. We have our f as a function of epsilon, and then we have a g of epsilon d epsilon. So that means that I have lumped all the terms apart from f in the integral into g. The g epsilon is the following object. It's L divided by 2 pi h bar, and then the square root of 2m over epsilon, and it has the name density of states. The density of states can be understood as follows. We have an equidistant grid, as we had seen, of k values, which means that if you look at the energies for each k vectors, that the energies close to 0 are very dense. There are very many states with low energies, and because the energy is growing faster and faster with increasing k, there are only few energy states in in the same segment on the k-axis here as there are there. And so if we sum over the case, we have to multiply, we can replace that by a sum over the epsilon, but we have to multiply each time by the number of states that is available in a small interval d epsilon. And precisely that number of states, so if we draw here the connection lines which give us all the energies, we see that they are more and more spaced. And if we sum over all the epsilons, we have to take equidistant intervals d epsilon, like this one, and that one, and that one. And we see that there are fewer and fewer states in such a d epsilon, and that's represented by this density of states. So GE is the density of states.